Lab 4 Oscillations. The purpose of this lab is to analyze the motion of a spring oscillating in 2 dimensions. There are 2 fundamental principles used in this lab. The first is Newton's second law. The 2 forces acting on our system are the spring force defined by Hooke's law and the gravitational force by the Earth. Newton's second law will be used to calculate important unknown terms in our system. The second fundamental principle is the energy principle. The energy principle states that the energy of the system is equal to the energy exerted by the surroundings. However, by setting our system to include the mass, spring, and the Earth, the energy from the surroundings will be equal to 0. The energies present in our system are the spring potential energy, gravitational potential energy, and kinetic energy. In this lab, we will prove that the total energy of the system is in fact equal to 0. Here is the video we are analyzing for this lab. By analyzing the motion of the spring tracker, we can compare the motion to that of a computational model. The mass and initial length of the stretched spring were given in the lab prompt. Here are the initial conditions taken from the lab prompt and tracker that will be used in upcoming calculations and coding. Our first unknown variable is the spring constant K. Using this equation for the period of a spring, the equation for the spring constant can be obtained. By taking the average of the periods from tracker, I calculated the period of the spring's oscillation. Plugging this into our equation, we obtain the spring constant. The second unknown variable is the relaxed length of the spring L0. Using Newton's second law and the fact that the spring starts in static equilibrium, we can set the magnitude of the spring force equal to the magnitude of the gravitational force. Using variables that are already defined, we can solve for the relaxed length of the spring. Looking at the code, the mass of the ball, the initial position, and the initial velocity of the mass were changed. The gravitational constant, spring constant, and relaxed length of the spring were also inserted. These lines of code were changed to specify the spring position. Lastly, the system energies were defined. Looking at the while loop, the initial energies are defined. The gravitational force and spring force vectors are specified. The net force on the system is then set to be the sum of the gravitational and spring forces. Using the momentum principle, the velocity and position of the mass are updated. The spring position was also updated within each while loop. Finally, the system energies and energy changes are updated. Notice that the total energy of the system is the sum of the kinetic energy and the spring and gravitational potential energies. Here is the video of the computational model. The blue ball represents the computational model mass, and the red ball represents the position of the mass from the tracker data. The red ball's motion doesn't look as smooth as that of the blue ball. This is due to the difference in time step between the computational model and tracker. Here is the resulting energy graph and the corresponding key. As you can see, the spring and gravitational potential energies oscillate inversely to each other. The largest takeaway, however, is that the total energy of the system, the sum of the individual system energies, is equal to 0. This confirms the energy principle and the fact that there are no interactions with the surroundings. Here is the corresponding position versus time graph. The position graph was x squared plus y squared because this represents the radial distance of the mass in 2 dimensions. The red represents the tracker model and the blue represents the computational model. As you can see, the position of the tracker model matches the computational model almost perfectly. This means that there was almost a complete avoidance of error throughout the completion of the lab. The first "what does it mean" question asks if the energy principle is satisfied. The answer is yes. Because the system was chosen as the mass, spring, and the Earth, there should be no significant interactions between the system and the surroundings. Therefore, the total energy of the system should be equal to 0, which is satisfied in our computational model. The second "what does it mean" question asks to compare the difference between the periods obtained using x position data versus y position data. The periods differ slightly. This is because the position of the mass during the oscillation differs between the x and y axes.